Okay, so we are going to call this the quick review after polar vortex of 19. Okay, that's what this lesson is going to be called. So we're basically going to refresh everything we've done, because at some point we're going to learn a little bit more, but then soon we're going to get towards testing. It's going to be still a week or two. You still obviously have your quizzes, but the big test where it's going to come down to like crunch time. So let's see what we started with. So let's thin that pen up a little bit. And let's go to estimating area. So we estimated area at one point, and generally we were given. Thank you. We were given some kind of shape on some kind of interval. So let's just draw one, right? Because we could just spend all day. So you basically just have to think about the shape and do that. Now, I could ask you questions like find the upper sum, and in that case, that would mean that you would have to calculate, using 5 rectangles from 0 to, that's a odd number. But then you would do an upper sum, and you're smart. You say, all right, well, that means I've got to be outside of the curve. So you end up, these are not to scale. You can end up drawing 5 rectangles, right? All of equal width, and then you do your calculations and you would estimate. Or I could ask you, use left endpoints to estimate the sum. And then you would do exactly what you've done. And then I could ask you, is it an upper sum or a lower sum? Long story short, without beating this down too much, just kind of look at the function, draw the rectangles, see what it's asking, length times width, kind of calculate the area of each individual rectangle and add them all together, so on and so forth. Remember, it can depend. I used a left endpoint there to get an upper sum, but then if I used left endpoints on an increasing function, then it's going to give me a lower sum. So think about things like that. So that's the sort of stuff we did there. Then we moved on, and we actually calculated exact area. Week, but by the time we got to the end of the week, we calculated exact area by doing infinity and represented the number of rectangles, and then we went for a summation of from a equals 1 rectangle all the way up to n, so that'd be infinity. And then this is where you got in trouble. Those that did get in trouble on the quiz, you still used your width, because eventually, you got your book definition, but we speak about it in class. It's going to be f of width I, so it's going to be b minus a over n times I, times the width, which is b minus a over n. And a lot of you put in a number for the width, but you can't. It's a sum, and you had to leave it as a function and distribute. What I'm going to say about this for now is that's generally what we did. And slowly you would plug in your b minus a over n in your I into the particular function. You would expand it as much as you could. And then you would isolate your constant, your I squared, and your I cubed. And you would plug in those formulas up on the board to the left there. And then you would work that out. Now, by the time we get to the test, I'll give you some review time. We're not going to go through one of those examples because they take a long time, but that's what we did. So, we can review that at test time, but you're finding the exact area using the limit notation, which was a lot of work. Then we went on and we went the short way. So then we calculated, we then worked, let's change color. We did work with any differentiation. Okay, I'm going to shorten it. Basically, indefinite integration, meaning the same thing. So what that means is you did it two ways. You had first of all, you've only dealt with two things at the moment because of our skills right now. You've dealt with polynomials and you've dealt with trig functions. And so when we integrated or anti-differentiated polynomials, that was just adding, add 1 to the power and then divide by power. Nice and simple. Then the reason it's indefinite is because there's a family of functions, all their vertical shifts. We had to add the plus c. All right, so that's important. We'll talk about that in a second. Then you've got the trig, and the trig is where we first start bringing the buzzword for this semester that helps you out when you get into trouble. Whose derivative is question mark. So, if you're given secant squared, you're like, oh, I've taken a derivative and its answer was secant squared. Whose derivative is that? What function gave me that as its derivative? And that's how you answer those types of problems. All right. So, and then you answer that with the whose derivative is, and then you add c because it's indefinite integration. It could be tangent plus 1, tangent plus 2, tangent of x plus 1, tangent of x plus 2, so on and so forth. Then, so we had the indefinite with the plus c. Then we went through, and now we did particular solutions. So that means we're no longer, that means no c, right? So you'll end up solving for your c. And I might give you an f prime. I'm just gonna just make one up for the fun of it, right? I might give you, negative. Let's just keep it positive. Give it x cubed plus 2. And then what you will do is you will find its integral, right? And I'm not going to show all the correct notation. I'm just going to do it, right? So f, which could be the integral. So it's going to be add 1 to the power. So it's x to the power of 4 over 4 plus 2x plus c. Because it's a particular solution in the problem, I would have said to you f of 2 is equal to 5. So that means on this curve right here, it's equal to 5 when I plug in 2. So then I could just plug in my 5 for there, and set. No, that's lying. I would plug in my 2. I'm so sorry. I just saw what I did. Okay. I'd plug in my 2, and then I would set it all equal to 5. So 5 is equal to 2 to the 4th over 4, and so on and so forth. Right? So nice and simple. Then we took it up, and we took it to the vertical motion problems. So let's do the first level of those. So then we're into vertical motion. And it might be a question. It might be a question such as a ball is launched at whatever 70 feet per second, or it might be 20 meters per second, and from 50 feet or from 6 meters, something like that. And then you are supposed to, they might say to you, what's the question? What is the velocity at time of impact with the ground? All right. So basically, we're going to talk about this several times throughout this lesson, but basically, you have this concept. You have the position function is the top rung of the ladder, and we've climbed all the way up. We're going to climb up from. Actually, let me mention this before I do that. At time of impact. So we're going to, you've got these concepts. You've got gravity. Gravity is a constant. It will either be negative 32 feet per second, or if you're dealing with meters, it'd be negative 9.8 meters per second. And then you've got your velocity function. You're going to integrate your velocity. Will be climbing up the ladder from acceleration. So you'll be going up one time. So you integrate acceleration. But it's always going to be, and this is where you try to get your bearings together as we come to test time. It's always going to be, velocity will always be negative 9, well, if it's negative 9.8t plus your constant of integration, and our constant of integration is always initial velocity. And then velocity in feet would be negative 32 t plus initial velocity. Sometimes it's easier to go down the ladder, so we'll have a look at that from the back side of it. So let's go and do position first. So now we're at the top rung of the ladder, which is the integral of velocity. And that's always going to be, you can integrate it and show it, it's always going to be, in feet, would be negative 16t squared plus initial velocity times time plus initial position. It'll always be that. Or it would be, in meters, it would be negative 4.9 t squared plus initial velocity plus initial position. Because let's look at it the other way. So now let's pretend we're going down the ladder. Okay, so we're all good with top ladder's position, middle ladder, I'm being lazy there, position, velocity, and acceleration. So here's position. So its derivative, so if you want to succeed, there's no way I can tell, right? Let's just honestly think about it. So its derivative will be 2 times 4.9, or let's do feet, 2 times 16, which gets you negative 32. And then it would be 1 times initial velocity. So it'll be initial velocity. So that gives you that. And that makes initial velocity a constant. And then you go down the ladder one more time to acceleration. Guess what? 1 times negative 32, and the derivative of a constant is just 0. You're down there. Those are super important to keep in mind. Sure, you can, this is the easiest level. So what's the velocity impact? Let's think about that. If an object impacts the ground right there, we have to keep in mind that this is the position and it hits the ground there. So you need to know the time it hits the ground. So basically, you have to, use your calculator, or you can use algebra, it's up to you if you want. Figure out when it hits the ground. That t, once you found that t value, you found it, then you plug that into your velocity function, and that finds the impact there. So those are all nice and simple, right? So I'm not going to spend too much time on those. If you've got issues on those and you're rewatching this video, definitely talk to me about it, right? Let's go to the other one. Now let's spend some time here, because this is one where I want you to focus in, all right? So kind of shake off. I'm going to write the concept here. This is basically the one that gave us trouble. Reach a particular height. That's fine. Reach a height concept. So we've done getting over the Washington, getting up to the same height as the Washington Monument, do these other things. Let's draw something out and run through it. So if I said to you, okay, I want to launch an object from, let's do, I want to launch an object and it needs to reach the height of something, which happens to be this height right here is, we'll call it 1,000 feet. This right here is, it's not to scale. We'll call that like 6 feet. It's like some person's throwing it, right? Let's go ahead and throw all of the rungs of the ladder to the next of it so you can see them all together. So we know the top rung of the ladder don't know what's going on. Here we go. The top rung of the ladder is position, and that is always, what are we in? We're in feet. So we're going to be negative 16 t squared plus initial velocity t plus initial position. And then you've got velocity. Velocity will be the derivative of that. So try and answer it in your head. Please say it out loud if you feel confident. But it's really important to think about. When I take the derivative of negative 16t squared, everyone should be comfortable in negative 32t. When I take the derivative of initial velocity t, that's 1 times initial, you don't need to say anything, 1 times initial velocity, reduce the power by 1, so it's initial velocity. And then I can go all the way down, and it'll probably be irrelevant for this problem, but I can go down to acceleration, which should be negative 32 constant. So let's look at a few other things about this curve. So now let me try and shrink it up a bit so I can get something else on here. All right, so let's draw out a little, see if how straight I can do this. Let's label this time. So this is going to be known as time. This is going to be known as your position. So yeah, that'll be the top rung of the ladder after you've climbed all the way up. We call it t. This will be a velocity function. We call that v of t. And this is your acceleration function, which is our a of t. So let's go ahead and take a couple of key points here. So we're looking at time 0 right now, just as the person launches it. So I want to find out, let me try and add, can I add a highlighter here? Oh, I see why I can't see it. It's over here. Right, so here I am, right there. I'm at that point in space. So the t value, which we're referring to, is this x coordinate right there. That's the t value we're talking about, the horizontal. So the time, when time is 0, we want to know the position. So that position for all functions will be s sub 0, initial position. Give me a number in this particular case. What number is it? 6. It's right there. It's 6. 6. I'll be careful with it. There's 6 feet. That's where we are. The velocity at the beginning is going to be initial velocity. And in our questions, we're asked, what is the initial velocity used to reach the top? So we don't have that yet. I'll do a practice problem in a minute, right? We don't have that. So we just have initial velocity. And then what do we have for acceleration? Well, that's always constant. So that's it. We're in feet. So that's always going to be negative 32. That's it. It doesn't matter what your time is. It's going to be traveling at that negative 32 feet per second per second. So, all right. So now let's go ahead and mark up this diagram. So let's go ahead and see what I like my green. So let's do. Like here we go. So here's this point right here, and I did that arrowhead for a particular reason. Okay, there's an arrowhead. Here's the black time we're talking about. We're right here now. Okay, we're right there at that time. So we will call that time left of maximum. So what's the position? The position will be whatever time you plug in into the position function, right? And that's all there is to it. Is that going to be useful at this moment in time? No, it isn't, right? But that's what it would be. What's the velocity going to be there? Well, what you know about that. Let me ask. Okay, so now ready? Just quick thinking, and I won't answer the question, but you've got just thinking about this. If you've used your physics, don't pretend you've got anything in your class. So the options are going to be they go together. There's going to be positive or negative, and one of those goes with these slowing or decelerating or speeding up or accelerating. All right. So at that point has to be one of both lines. It has to be positive or negative, and it has to be slowing or accelerating. So that green dot, to fully understand this, important, is that dot, let's start off with positive or negative. Say it one more time. I think I heard both. It's not negative. No. So there's a good thing. All right. So here is quick reminder. If objects are traveling up or to the right, their velocity is positive. So yes, up or to the right. If it would then be positive. So that is that ball at the moment traveling up or down? Up, so it's positive. And then if you're going left or down, velocity will be negative. Velocity and speed are the same thing, except velocity has direction. It goes up or down, left or right. So now, is that ball slowing or is it speeding up? Is it accelerating? It's slowing. What force is acting on it to slow it down? Gravity. Exactly. So if you keep all that stuff in mind, everything's going to work out well. So it's slowing. So it is to think about that. So we got like, okay, so we just said our velocity is positive on the way up, but it is slowing down. What is acceleration due to gravity at that point? It's pulling down at 32 feet per second per second. It depends on the strength of the ball, how quickly it's pulling away. So it's always a tug of war between your forces. And we got to go over this because we have a lot more things. Like, I'll talk about later. Just keep going with the flow. So, all right. So now here's the huge one. So let's go back to green. So we're now I want to be at the maximum. I'm at this maximum right here. So let's think about that. What is what is the position function of that maximum? Well, it has a point on that maximum. It has a point time t. We need it to reach the top. We need it to reach the height of our object. So we need that to be time t, height 1,000. Now, this is going to be important because we have our systems of equations to set up. So we've got a point on that. What is the velocity at that time? So let me ask you. So we'll jump ahead. Let's go back to the right of the maximum. Come on, maybe I can just shrink it. Okay, so let's go to the right of the maximum. I meant to be in green. So I'm over here. The ball's heading down like that. So we're on the right of max. The position is whatever it is. Is the velocity positive or negative? Going down, so it's negative. Is the speed accelerating or slowing down? Accelerating. It's traveling at, it might be traveling at -5 feet per second. Then it might be it's going fast at -10 feet per second and 20 feet per second. So it's accelerating in a negative direction. And acceleration due to gravity is constant, doesn't change. So go back to the middle. Like now we're back to this maximum. Let me ask you a question. If on the left of the maximum the velocity is positive, and on the right of the maximum the velocity is negative, what must the velocity be, which happens to be the derivative of position? What is the slope of the tangent? So hopefully I said all those things together at the top height. Yeah. 0. Perfect. And then acceleration doesn't change. So also what we know there is if we know, let's do this one in red because it's crucial. This maximum for these types of problems, for it to reach there, I've got unknowns. I will have to know what I'm going to have to know to find that initial velocity. I'm going to have to know the time and the initial position to find that point. And that time will be found from this. Because I know on that curve, this is the velocity, that's that red point, that's that tangent right here. That lies on that graph. This function, -32t plus initial velocity, looks like that. It's a line driving downhill. We want to know the time that is equal to 0, the time that there's that flat tangent. And that time, we want to know, when does that function equal 0? Well, when does it equal 0? That's the 32, if you don't mind me squeezing that in there. And then subtract initial velocity, divide by -32. So your time equals v sub o over 32. Now, in Algebra 1, you probably wondered, why are they making me solve so many lines, solve for x, plug it in for y, then go back and solve for y? Well, this is the exact reason, right? Because you've now eliminated a variable, and so you're going to substitute in another variable for it. So you're going to replace this t right here with initial velocity over 32, and that's going to be a height of 1,000. Because now, think about coming up here. So now I use this highlighter. So currently, in this equation, you've got your position, you don't know. You've got your t, you don't know. You got your initial velocity, you don't know. And you got your initial position, you don't know. But if we go through and ask them, all right, so we've looked at it. We know initial position, right? So I've got that. So I'm going to take that yellow line off. That initial position is 6. So I've got that. So now I've got that. That's not an unknown. I still don't know the initial velocity. That's good. but I don't know the time. But now, guess what? I've solved for time in terms of initial velocity. So I will be able to go back and plug that in. So that will look like this. So that will be negative 16 initial velocity over 32 squared plus initial velocity times initial velocity over 32 plus your initial position. Now look at it. Now I've got initial velocity over 32 and initial velocity over 32. I've only got one. Oh, my position. Well, guess what? You need that to meet your 1,000. So you've now got the only thing you have to solve for is one unknown. You've got it all the way down to one unknown, which is algebra 1 level problem, right? So you're good. And at that point, plug it into your calculator. I'm fine with that. You don't have to show any algebraic calculation. I just solve it, right? So then, good to go. And then concept-wise, the rate of the maximum is negative. Its position is negative. It's accelerating. And then, last but not least, when it hits here, when it hits the ground, well, what is that? So let's say, when it hits the ground, so what's its position? 0. It hit the ground. It's 0 feet above the ground. What's its velocity? It's of t, whatever time you hit the ground. From that, it's a parabola. All you do, I'm starting to rush it, but I want to make sure I know you're getting tired. You're on a simple parabola. We want to know when it hits the ground. Algebra 2, plug it into your calculator, calculate intersection, whatever you do, find the t. Plug that into your velocity function. And then what's acceleration due to gravity? Still negative 32. All right, I think that's enough for me to stop talking. So the only reason I'm talking is so I don't go to sleep. So here we go. So I want you, I'm going to abbreviate. I'm going to try and leave that on the screen. Actually, I'll do it over here. I'll just leave that. All right. You're going to try one of these. So I want you to do for me, abbreviate it. Okay. So you've got an object. You need to, the question is find the initial velocity required to get an object shot up from 5 feet to reach the top of a 900. Actually, should I mess with you a bit and do meters? No, let's just keep it. Let's do 900 feet, 900 foot object, 900 foot building. I need you to find the initial velocity needed to reach the top of a 900 foot building, please. I'm just going to stop the video because that will be just independent practice. And then we can do more if we have time, but I think we'll be good with this.